There are many different ways an equilibrium can be shifted or stressed. And there was a guy, his name was Le Chatelier, and he came up with this theorem that if an equilibrium is stressed, the equilibrium will adjust in order to reduce that stress. And that's called Le Chatelier's principle. Now, we can predict the direction of a reversible reaction depending on what stress is applied. If we change the concentration of an equilibrium, let's say we increase a concentration of one of the chemicals in an equilibrium, the equilibrium will shift away from that increase in concentration. If we remove a substance from the equilibrium will shift towards that removal. Depending on which side each of those chemicals are on, we say that that is either shifting left or shifting right, shifting towards the reactants or the products. For example, with this equilibrium right here, if we have hydrogen gas and iodine gas reacting to form 2-hydriodic acid gas, and we end up increasing the concentration of the iodine gas, let's say. If we increase that concentration, the equilibrium will shift to the right away from that increase in order to form more products and reestablish that equilibrium. Changing a pressure will also change an equilibrium or shift an equilibrium, and especially for gases. Now, if we increase the pressure of a gaseous system that is at equilibrium, we will shift the equilibrium towards the side with the fewer number of gaseous molecules. So, for example, this equilibrium here, 2NO plus O2 reacts to form 2NO2. The reactant side has 3 moles of gas, and the product side has 2 moles of gas. So if we increase the pressure, either by applying an external pressure or by decreasing the volume, we will shift this equilibrium to the right to produce more of the product because we will favor the side with the fewer moles of gas. In this reaction here, N2 plus O2 reacts to form 2NO. We have 2 moles of gas on both sides. Because we have 2 moles of gas on both sides, pressure change isn't going to favor either formation. There will be no change. Temperature can also change an equilibrium, but you have to know if it's an exothermic or an endothermic reaction if you're going to be able to predict whether you're going to shift or not. So if I'm looking here I have an exothermic reaction, and we know in an exothermic reaction, heat is a product. So I'm going to write heat over here because we are exothermic. And then we add additional heat to this system. That's like saying we're increasing this concentration. Remember, we shift an equilibrium away from an increase. So adding heat to this reaction will shift the equilibrium towards the reactants or shift it left. Conversely, if we had an endothermic reaction, and here's an example of an endothermic reaction where delta H is positive, then heat is a reactant. If we increase the temperature here, we're going to increase this piece of the equilibrium, then we will shift the equilibrium away from the increase. So in this case, for this endothermic reaction, by increasing heat, by increasing the temperature, we are shifting the equilibrium towards the right, towards the production of more products. Remember, even though this is an equilibrium, the left side is the reactant and the right side is the product. The reaction, as it's written from left to right, is the one that we're measuring to be endo or exothermic. The system will only be one, endo or exo. It will not be both. If you have a catalyst, that will not affect the equilibrium. It doesn't affect the equilibrium because although catalysts will speed up the rate of a reaction by decreasing the activation energy, that works for both sides, both the forward reaction as well as the reverse. So a catalyst will speed up the time it takes for the equilibrium to be established, but won't actually affect the value of an equilibrium constant or the concentrations. So when we have an equilibrium, that equilibrium can be stressed or disturbed, and it can be stressed by changes in temperature, concentration, and if we have a gaseous system, volume and pressure. Remember how volume and pressure are correlated with our gas laws. So if we increase the pressure, we're decreasing the volume, we're going to favor the side that has the fewer moles of gas. And this table here, the table 1, effects of disturbances of equilibrium, might be good to refer to until you get used to how these things shift. But there is not going to be a change on the value of K, the equilibrium constant, unless there's a change in the temperature. But we'll get there eventually. You don't need that right now.